checking your agenda with Boston and checking out when lectures change. So, what we're gonna talk about today is actually two lectures that both talk about ways of doing polymorphism, ways of building code which is substantially generic. Now, first lecture will be about subtype polymorphism. We'll go beyond the idea that to use a value where a value of a given type is expected, the type of what we give has to have the same type of what is expected. So, then we'll show a way to define our own type inequalities. And finally, I'll show a couple of examples on building lists and state machines, or perhaps this will go to the next lecture because it's a long live coding demo. Now, in the previous lecture, we have seen that Java and C# have a static type system. Moreover, what the direct implication of this was is that programs that make no sense are refused by the compiler. And making no sense refers to calling methods or making assignments where the right-hand side of the assignment, or the argument of the method, and the variable being assigned, or the parameter of the method, are not the same. Okay? So this was the fundamental concept. So, which can be summed up with: you expect an int, you are given an int. You expect a float, you are given a float. You expect a t, you are given a t. Okay? So that's the whole concept, right? Okay. Now, so obviously, if we expected an int and we get a person, well then clearly something was off and we expect a compiler error. And not only do we expect it, but we actually welcome it because it tells us, you have made a clear mistake. A person and number are not the same. And the two most important typing rules that cover these violations are those of variable assignment and method call. Because those are the two places where we make the most vehement check for equality. Specifically, you were hoping this would happen, right? Yeah. Now, specifically, we assign to variable x an expression e. What we really want is that the type of the expression is equal to... Yes? I'm hearing it from the crowd, vaguely.
Declaration.
The declaration of x. Yes. So this is just what we said. And the other rule is nothing special, no panic. The parameters we give at the same type as the parameters we expect. Okay? This is all. This is literally all there is to it. So, this program violates the first typing rule. Because this has type. And where do we find that? In the declarations. And this is a constant string as type string. Good. Similarly, if we call the increment function, which expects an integer, with a counter, you also see why this makes sense. Oh. But on the so also, if we say something like int x is equal to 5.5, this also makes no sense. Why doesn't it make sense? It's a float. So, with respect to what we've just seen, the types are different. Okay? So we put a double where we expect an int. Also, logically, it doesn't make sense. Why doesn't it make sense logically? Come on, look at it. Is 5.5 an integer number?
No.
What are the two options that we would have to make a conversion? No, but I mean, let's say I want to put 5.5 into an int. 5. I could put 5, he says, or 6. Or 6, okay? But are 5 and 6 equal to 5.5? No, they're close, but they're not the same. So that seems like a big decision. I mean, you don't just take 5.5 and say arbitrarily, yeah, this is going to be 5. Or yeah, this is going to be 6. So you actually have to let the programmer make a decision depending on where you want to go. So maybe this makes sense. What about a similar expression like float x is equal to 10? What is the type of 10? Int. So according to the rules that we have seen in the previous lecture, this should fail. does it make sense that this should fail?
No.
Why not?
Because if you convert it to a float, it will be 10.0, and that's exactly.
That's exactly the same. So it does make sense in some cases to promote a value of a data type to another type, as long as they're the same. So, are we losing information here if we convert 10 to 10.0? Does the point 0 carry valuable information? No, it's exactly zero information. Well, it is a new type that contains the same value. So, the idea is that floating point numbers, in a sense, contain integers. Can someone make an example of an integer that is contained as a floating, that is also a floating point number? 2. And what floating point number is it? 50. 50.0. 80. 80.0. So every integer that we might choose, that might tickle our fancy, can be converted freely in the sense of gratis, into a floating point number. We just add a 0.0. We are not losing information. Okay, so the typing rules so far are too restrictive, because we should be able to accept an assignment for a data type which is more specific, like int, into a data type like float which is less specific. So, now actually, what do you think more specific and less specific? What do you think that means? Camera, watch it. Watch the camera. No, as in don't go. Yeah, don't hit it. Okay. So, what do you think I mean by saying that int is more specific than float? In the range of... What do you think more or less specific means with regard to two data types?
An int is more specific than a float.
Yes.
Wow.
I know that.
That's more room to play, right?
Yes. Yes. Let's take a range. Do you want to say something?
A float.
No, he wants to say something. He's always quiet, but he has lots of right answers. Yes.
Oh, I thought an integer doesn't have neat pointed information, so it's more specific than a float.
To an extent. But, yes.
If you have a number, a float can be even higher than the possible number. While an integer can, so integer is exactly that number, while a float could be even less.
We are really getting there. Consider an arbitrary range with an integer, from 0 to 10. How many integers do we have between 0 and 10? Extremes included. 11, right? How many floats do you have in the range 0 to 10? Infinite, no, but I would guess more than 11. 11 times 10, are you sure?
11 times.
Nah, a lot. A lot. Technical term is a shitload. It's a range where float is also very precise. So you have 0, you have 0.01, you have 0.02, you have 0.0001, you have 0.00001, and so on. So to get in floating point numbers from 0 to 1, takes way more than 11 steps. We're talking about hundreds of steps, okay? Got it? So in what sense is it more or less specific? Because, well, we have, you could imagine, more or less integers than floating point numbers. Sorry?
Less.
Less? What? Which loses? Oh, sorry. Less integers than floating point numbers. Exactly. We have less. So, and moreover, every single integer is also a floating point number. So, these two things together. Focus on these. We have less integers than floating point numbers. And for every integer, we have a floating point number, which is
0.0.
yes, which is the same value. So every integer is also a float, but we have more floats. Got it? So how would we draw this if we were 6 or 7 years old? We would say these are ints, and where are the floats?
Around the int.
All around it. Actually, I'm saying floats here loosely, but this is double. But the idea still stands. Okay? Got it? Not yet. Okay. Yes? Now, let's introduce a new concept. Consider two data types, T and S. Maybe whatever we want. We say S smaller than double point T. There's more spaces than there should be, but doesn't matter. So S is smaller double point T, and we read it. S is a subtype of T to mean that any value of type S can be safely used where the value of type T is expected. Think always about ints and floats. Any value of type int can be safely used where the value of type float is expected, right? Because it can be converted. You just add 0.0 to it, right? We also say that T generalizes S. So to generalize, you have to add information. So float has more information than int. So float is more general than int. So int is a subtype, wait a second, is a subtype of float, because any value of type int can be safely used where the value of type float is expected, because the conversion loses no data. So we can safely convert, because there is no danger. Now, we can now amend all of our typing rules that require equality. So instead of type equality, we can now use subtyping to preserve safety but achieve more flexibility. So what has changed here? Yes. Yes.
You said that int was more specific than a float?
Float generalizes it. Yes. This is just standard terminology. So I'm just broadcasting it from someone else that said it like 50 years ago.
T is part of the declaration of X.
Yeah. Come on.
The
Yes.
declaration is a subtype.
Precisation. Yes, 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 yes.
So T is a subtype.
Say it again. Say it again. Okay.
The declaration of X is now a subtype of T.
Actually, the other way around.
Uh,
T has to be a subtype
and
of whatever the variable was declared. Okay? So the only thing that changes is here. This was equals, and now is smaller equal than. That actually means, if you want, you can see this. Some other authors, instead of smaller, instead of instead of smaller double point, they use smaller equal, which kind of makes sense because int. Come on, isn't int smaller or equal than float? That's a smaller equal. You know, like 3 smaller equal than 5, or 3 smaller equal than 3. Yes? No?
never seen it in my life. Sorry.
Kidding me. No, there is no.
No.
Possibly be. No, wait. You have never, when you write this, have you ever written this in Python?
Yeah.
Okay. And you have never seen this in mathematics?
Yes.
Did you go to school?
Yeah. No.
Then, there you go. Now, do you realize why we would want to say, why the intuition of this symbol subtype is such that we could say int is smaller or equal than float? Do you get why?
Because int is always ending at a 0 and the float can be 0.1.
Yes, exactly. And so literally, if you take all the integers and take all the floats, there is more floats. Literally, there is more floats and every int is int float. So it's also the concept of sub. No, in sets. Subset. That's literally the concept of a subset. So, similarly, What has changed now when calling a method? Oh, come on.
Equal sign replacement.
Yes, the parameters we give can be more specific than expected. So if you have a function that expects a float and you give it an int, yeah, it still makes sense because function calls are just assignments because you are literally just assigning the parameter of the function with the value you put in there. So that's it. Now, oh, this is all fine and dandy, and we have integers and floats with this nice conversion. Perhaps we could define our own classes that make use of subtyping. So when we define our classes, we might want to say, you know what, this class, well, right now you have two classes like, I don't know, player and mage, and then archmage, okay? And, well, is the mage a player? Yes.
Player can be mage.
Yes, exactly, but every mage is going to be a player. That's the player class. But the archmage is also a mage, right? But therefore the archmage is a player as well. But right now, if you have three classes, player, mage and archmage, well, they are three different things. If you expect a parameter of type player and you have a mage and you want to give to a function that expects a player a mage, it kind of makes sense intuitively, but we can't do it. We are prevented from doing it. But what we want to do, and what we achieve, the ability that we achieve thanks to subtyping, is exactly the ability to do this. So, let's think about a few examples of classes that generalize each other. Come on.
So if you have a player and
All corgis are dogs, but not all dogs are corgis.
Sorry?
All corgis are dogs, but not all dogs are corgis.
So, all corgis are dogs. Yes, corgis are dogs. Which is the subtype of which?
The corgi is a subtype of dog.
Corgi is a subtype of dog. Yes, exactly. Something else. Come on.
Car is subtype of vehicle.
Car is subtype of vehicle. Yes. Come on. Something else.
Pretty late.
Okay. Now, so this is another example. So this is generalizes and subtype of are. What's the relationship between generalizes or being a subtype of? Other way around. Okay. So a person is generalizes a student. So you are all persons to my eyes to an extent. Okay. Light meter generalizes lamp. Animal generalizes dog. And so on. So, if you have a method, okay, somewhere that expects an animal, would you like to be able to give a dog to this method?
Yeah.
Would you like to be able to give a tiger to this method? Yes, it makes sense. Okay. Now, for example, which generalizes which? That's between Mercedes and car brand.
Car brand.
What? Say it out loud.
It's a subtype of partner.
Mercedes is a subtype of car brand. Now, living space versus apartment. A tent is a living space.
Generalizes apartment.
Living space generalizes apartment. Notice that the greater than symbol is by the generalization, so it's an ordering of generalization. Cat versus bird. No.
that's funny.
Tenzij we over de food chain praten.
But do they have a relationship? Are all cats birds or all birds cats? Yes, but eaten by is not.
Ja.
So they have no direct relationship. Now, mind you, they might be things that can be eaten by lions. Both of them. They might have a common ancestor in a hierarchy of generalization. They are certainly both animals. But they are next to each other, not one above the other. Person versus employee. Once again, person generalizes employee. Okay, so it makes sense. All employees are persons, but then you might have some persons that, yeah, I don't know, are not working or on a pension or whatever. Student versus person.
Person is a subtype of student.
Person generalizes student. So the other way around. It doesn't matter if you get the terminology wrong, but the point is all students are persons.
I know.
But not all, yeah, but not all persons are students. Which makes sense. No, come on. You are all people. Really. Give yourself credit.
You clearly don't know us well enough.
I'm willing to go out on this assumption.
I'm not notches.
Student versus employee.
Equally.
I would say neither.
Sorry?
I would say neither.
What do you say?
Okay, we can both.
Hi, welcome to the lecture. What do you say? Neither. Yes, they have no relationship. Now, on the other hand, consider this specific relationship. So the person is a generalization of the employee, the person is a generalization of the student. So we could obviously imagine that, well, what are person, employee, and student going to be as we implement things? Classes, right?
Or, yeah, interfaces.
Yeah. Well, the employee understand. They might also be interfaces actually, but that's a bit besides the point. So, but we get to interfaces. They are classes, and well, you might imagine that the person has something like a name, a surname, an age, whatever, and then the student will have, I don't know, a student number and a number and a hopefully non-empty list of exams passed, right? Whereas the employee will have a list of tasks or a manager or whatever. So. And what we want to say is that we have these three classes, person, employee, and student. Person and employee has to be somehow related. So we have to tell the language somehow that every employee is also a person. Okay? And the same goes for person and student. So every student is also a person. How do we say this? We use a mechanism which is called class inheritance. A class like employee will inherit from class person. This means that employee, this is a very important sentence, makes or breaks the lecture actually. When we inherit, I'll show you the syntax for inheriting, which is kind of pointless, what it does is more important. The employee, if it inherits from person, will automatically have all fields and all methods of the person. So if the person has a name, and employee doesn't have a name, but inherits from person, does the employee have a name?
Yes.
Automatically. So if you have a class like student with 50 fields and 250 methods, okay? You will not pass the exam, but the compiler accepts it. Then you write the employee, which inherits from person and has one more method and one more field. All the ones of the person are automatically kind of copied and pasted invisibly into the employee. When we use inheritance of person from employee, then the language so inheritance, which is a language mechanism, so it's like a technological mechanism, automatically, when employee inherits from person, then also person becomes a generalization of employee. Okay? So the relationship that we have seen before is automatically built-in inheritance. So inheritance is a way to control and add our own instances of the generalizes relationship. So this means that anywhere in the language where we expect a person, we can now give an employee. This provides what is called polymorphism. Because, do you know what polymorphism is? What it means, the word? You know what poly means? Multiple. And morph?
To
Change shape.
Shape. So it means multiple shapes. So if I give you a person, what could it be indeed?
Big person, small person.
Now, think about the example that we've just made. If I give you a person, it might be actually just a person. What else could it be? A student or an employee. So if I give you a person, the person might have multiple shapes. It might be a person, it might be an employee, it might be a student, it might be a manager, it might be... Well, is there a limit to what it could be?
That you can think of.
As long as
It's still a person.
it inherits from person. Okay? So whenever you build an application in the presence of polymorphism, what you should assume is that what you get is not exactly the same as what you expect. Is at least what you expected, plus potentially something more. Inheritance requires very little code. In C#, just a colon. I'll show you. And in Java, the keyword extends. You may inherit from one class, at most another one. So you can't inherit from two classes. So you can't say that an employee is a person and a payroll entity. If payroll entity and person are both classes, you can't inherit from both of them. So this is what it looks like. Now, we declare class A with a method M. Then we declare class B on line 7. And what does B say? That is, exactly. So, the double point means it inherits. Therefore, B is a subtype of A. And A is a generalization of B. Because we have more A's than B's. Every B is an A, but not every A is a B. Got it? Now, on line 11, we can now take advantage of this mechanism. We declare variable B with type. We type A. No, sorry. Sorry, friendly fire. Can you throw it at him? Throw it. Now, on line 11, variable B is declared of type A. No, it's of type A. But we assign to variable B, what is the type of this expression? If I create a new B, what is the type of a new B? Yes, who said it? Yeah, it's a B. Obviously, you create a new B, what type has it? B. If I give you a new car, what is it? Probably a car. If I give you a new B, what is it? It's probably a B. Okay. Now, on line 12, we can say console.writeLine b.m. So, why does that work? Why is that acceptable?
Because we inherited the method M from A.
Yes. So M can be called just like that. Now, is there somewhere within the heart of B also a method N of variable B? Who said yes? Why do you say yes?
Because you declare it.
Not to declare it, you create it
Yeah.
as a B. So when you create it as a B, it will also store anything that we have here. Right? But do you think we could say here B.N? Who says yes?
You just gotta.
Who says no?
You just place it.
Nobody? It might surprise you, but we can't say N there.
And B put A plus N.
There is no N in A. And what we just said here at line 11 is that variable B has type A. So we are forgetting that variable B has been created as an instance of class B. By virtue of this here, what we're saying is that we will constrain ourselves to treat variable B as an A. This is very important. Once you go upcast You never go back. So the moment you say this is an A, what you're saying is that this is an A. So here you can't call b.n anymore. Yes?
Why would you do that? Because you created a new object B that you can't access things from B.
Yes, that's the idea. This is a contrived example. It's to fit in a slide. The point is, if you build a piece of code that expects a person, I give you an employee, you can't call methods that are of the employee. So this is the same thing. I'm writing here. I don't know what this is going to be, but I don't know if this is going to be exactly an A or a B or a C or something else. But what it is at least going to be is an A. So you give a lower bound, it will contain at least the information of an A. Perhaps more, but I will not be able to access it. It's just there, yes?
But why would you make it a B? Well, that's
In this case, this is idiotic. This makes no sense, the example. Yeah, you can guess that from the one-letter names that it makes no sense. But look, I'll give you the 5-year-old example. Class, animal, public, void, no, public, string, verse. Wait a second, does an animal make a verse? Dog. Turn. No. Okay. No, wait a second. Oh, I was better off with interfaces. No. Yes, okay. Public string. Get name. Ha. And return animal. Okay? Then on the other hand, we have the dog, which is an animal. We have the dog, which is an animal, and the dog also has another method, which is bark, which says woof. Okay? Good. Now, suppose we declare somewhere an animal A. Now, if console.readline starts with 1, this means that we want just an animal. So we say A is equal to new animal. Otherwise, we want a dog. And finally here, we write A dot get name. Now, should I run this program? What would happen? Besides the fact that it's always going to print animal. But what happens to A? Is A an animal or a dog?
Depends on the
It could also be a dog. But so on line 37, what do you know about A?
It has get name for sure.
You know for sure that it has get name, right?
Yeah.
But does it also have bark?
You don't know.
You don't know. It might, if we end up in line 35. But what if we end up in line 32? Will we have a bark method? Shall we? No, we shall not. So this is the idea. If you know that you can get away with only the things of the animal, in this context, then why not? You just need to know that it's an animal. Got it? Now, I'll show you another example which I think might be interesting. So static void, say my name, animal A. And then, okay. Now, suppose on the other hand that this is a dog D. Can we call method say my name with a dog? Can I put D here?
Yeah.
Oh, that's a recurring theme actually. Can I put the D here?
It's a dog D somewhere.
Where's the lipstick?
Can I put the dog as a parameter of, say, my name? Yes or no? Come on.
Yes.
I think so.
It's safe, right? So that makes sense. If I also have an animal, so I have an animal and I have a dog. So animal A is a new animal. Can we say the name of the animal? Obviously. Even more so because, well, parameter A is animal. At this point, look, outside the function, we also have bark. Can you begin gaining an intuition of a few more uses for this thing? So, according to say my name, dog that we give at line 37 is seen as an animal. Because say my name doesn't care. It could work for an animal, it could work for a dog, it could work for a cat, it could work for anything. But on the other hand, after we called say my name, which notice, this is powerful, we are reusing the code of say my name, which is not that relevant, but it could be much longer. We are reusing it for an animal and for a dog. Then after we are done with say my name, we can move on. And now outside the function, dog is known as a dog. So inside say my name, dog is seen as an animal. But outside of say my name, we do actually know that dog is a dog. We can make this a little bit more interesting, so we could say string animal, and then get name returns animal. And here in the constructor, well, generic animal here, and in the constructor of the dog, we could initialize. Do I have? Oh, sorry, stupid name. Do I have name here at line 22? Do I have this dot name? What do you say?
I think so.
Yeah.
We should have it. Why should we have it?
Because it's
Yes, because it's an animal. And notice that we have name. And name will be Fluffy. Seems a reasonable name. Okay, now as we run this, we get generic animal, Fluffy, and then Fluffy says, woof. Well, you know what? Much better. Okay? Good. Now, in Java, it's a bit terrifying the difference. Line 6, instead of the double point, you have extends. It's a little more verbose, so you get wrist string sooner. But, yeah, for the rest, the concept is the same. Now, suppose we were to run the declarations of this. Now, as we run the declarations, we will have two classes. Notice that. One class, I do want you to look closely at this. One here. Oh, can you see? Put it across this. Nope, doesn't work. Now, can you reasonably see? Okay. Notice, A has a bunch of methods. It has this, which is... Sorry? This is the constructor. Takes an A, which is this, and when it's done, it returns it. Then what do we have here? We have method M. Well, why? Where did we declare method M? Online? Yes? Line 4, yes. We take as input an integer, and also takes as input an integer and returns another integer. Why do I say it also takes an A as input, the method M? What is this A that M also expects? Yes? This. We always have this here. Now, on the other hand, let's go take a look at B. Okay, now B has, obviously, first one is, yes, the first one is the constructor. Takes this, does stuff with it, and then returns it. Then we have, oh, the second one looks weird. Very weird. What does that mean? M inside B. But we don't have an M inside B, or do we?
Yeah.
Yes, we do. But this method M, well, it will get a B and not an A as this. How come does this does work? Method M here was built for an A, right? But when we say b.m, we are actually here calling M with this. But this one here is a B.
Because you inherited A inside B.
And so, even if this is a B, is every B also an A? Yes, who said it? Every B is an A. So even if M expects an A, and we give it a B by calling, and it's fine, because every B is an A. So the B that we call on, that we call method M on, is also an A. Finally, quite straightforwardly, M is a method declared on line 11 that takes as input this, which has type, because we're inside B, yes, then an integer called y, and then it returns an integer. Okay? Then, on line 16, on line 15, we add a variable b with type a. So we don't look at what we have actually put in it. We just, all we know, all the compiler tracks, is that b has type a. Moreover, well, actually, to validate line 15, well, the type of this expression we said is the type of new b, the expression. Sorry? No.
New B is a B.
New b is a b. And the reason why line 15 is accepted is because that we are trying to put a b inside an a, which can be done because every b is also an a. So we're kind of just accepting that we will forget the specificity that this b is a b, and we just accept to treat it as an a for the time being. Then we move on line 16, and we have to check what happens when we call b.m of 5. Now the this of the that we give to the method m has type a. As we call b.m, what m wants is that here, left of the dot, we have something of type a, or more specific than a. And is this the case? What is the type of b? It's of type a. So this a here, we find also in the this within method m. The argument that we've given to m has type int. Which argument have we given? Where does this arg1 of type int come from? Sorry? Int? That is int x. It will be compared with int x. But who is arg1? Yes?
It's 5.
It's 5. That's the reason why I call it arg1. Because it might not have a name. And in this case it doesn't. And this is what we get. Which is obviously an integer. Okay? So what will be printed is therefore an integer. Then line 17 we're done.
Sure.
Yes?
Why
It
would
looks
you-
very much the same. Wait a second. Why did I put it twice? I have put it twice. Oh no, this is the execution. Sorry. Yes?
Why would you create a B if you afterwards save it as an A?
I said it before. This is a contrived example. So
And with contrived you mean
that is just to show the mechanism, but it does make sense. Now this one makes more sense.
Yeah.
So this one makes more sense because it allows us to write this function, say my name, which will work for anything. It works for an animal. It works for a dog, it works for a cat, It could work for, I don't know, Walter White. Yeah, come on people, seriously, who gets it? Yes. Okay, so this one makes sense, because say my name, this implementation here, as innocent as it may look, is capable of working for a gigantic variety of possible concrete implementations. Got it? So this is where you would do it, on a much broader scale. Now this is absolutely, you would never do it like this, okay? Now, on the other hand, so let's run this. Program counter starts at 15, we allocate on the heap allocation. Now, what is the type of this thing here? What is it? Is it an A or is it a B? Sorry? B. A way to make this prettier, should you choose to, is to write here that this is a B. Okay? You could even say it. Because actually in memory, the machine is going to store in the heap that this is a B. It actually has another attribute which I'm hiding here, which is the name. Which says the name of the class, sorry, the type, and it says my type is B. Because dynamically we need to know what method to call. Then, as we move on, oh yeah, we initialize by jumping into the constructor. This I'm gonna skip. Okay, when we get to calling b.m, now we still know on the heap that this here is a B. By knowing that this is a B, we know that everything, all the values, all the fields of reference are the fields stored in a B. Even though explicitly here we can only call the ones declared in A. So, knowing that B, which is a reference one, has type class B, we can call method m, and we'll jump into line 5, return x plus x, etc. So this is all quite straightforward as this is something you just know. This doesn't change anything actually. The behavior of these things remains exactly the same. Just literally exactly the same. Now, something that we have seen already with the say my name method is that if we have a method that expects a parameter of type A, wow, it's linked. We can accept a parameter of type C as long as obviously they are related. So, but unfortunately, not all combinations are allowed. Wait a second. So, I do want to read this through because I'm seeing something weird. So let's verify whether or not this works, whether this works or not. Do you think it works or do you think it doesn't? Sorry?
Doesn't work.
Because it says there?
Yeah. Yeah, also, but...
Let's assume I might have made a mistake.
You declare a variable of type, well, you make a variable, so you allocate of type C, but you say it is type B, and since both B and C inherit from A, they are not inherited from each other.
So, what line 6 is saying is that every B is an A. What line 11 is saying is that every C is an A. But what does that say between B and C? Absolutely nothing. So this is, what concrete example have we seen already that looks like this?
The cat and the bird.
The cat and the bird. So A would be animal, B could be
Bird.
and C could be. There you go. Both bird and cat are animals. That's completely random, by the way. That was not planned. That's absolutely awesome. Okay, so if I give you an instance of C, what methods does it have? I give you a variable of type C. What methods does it have?
O or 0?
What do you think?
O.
Yes.
O.
M and O. if I give you a variable of type A, what methods does it have?
M.
Just an M. And if I give you a variable of type B, what methods does it have? M and N. Yes, absolutely. So the problem here is that there is no inheritance relationship and therefore no subtype relationship between B and C. Obviously in Java this would become just with the extends instead of the double points. Now, the subtyping relationship is transitive. So this means that if we have X subtype of Y and Y subtype of Z, then X is also a subtype of Z. Would you dare make a kind of real world example for this?
Factory and I.
Sorry?
Eagle is bird and bird is animal.
So animal, bird, eagle. Okay? It's a very classic one actually, but it's fine. Come on, another one that is less textbook.
I container, I factory.
Car, Mercedes, car, wheel, car.
Yes, also. Okay, now, for another contrived example, now here there are not animals and birds and cats. Now, class A, no actually, look at, tell me why this works.
Because C inherits from B and also from
And then B also inherits from?
A.
From A.
So
So,
automatically.
what this means is that every C is a B, but every B is an A. So every C is also an A. This is perfectly logical, isn't it? Okay, then we move on. Then we really move on. Oh, no, wait. Now, as we said, A has method M, which uses an A that is that, what is?
This.
Yes, thank you. Who said it? Thanks. Then it takes an int, which is X, and returns an int. Then B has method, obviously M. Within M, the first parameter is this of type B, then an integer, and returns an integer. Then we have method M. M has a this of type A. Why? Because it is inherited. Yes, if it is inherited, look, it looks a bit like a sore eye. So, look, it looks different. This has another type. Why? Because it's inherited. Finally, what is C going to look like? M and O, yes. Yes. And the this of M will be A, the this of N will be B, and the this of O will be C. Oops. There we are. Okay? So writing this will be the hardest thing you have to do at the exam. Not kidding. So, well, pay attention at least. And for the rest, the calling of method M simply validates that the parameter, which is in this case the first parameter, where is it? On line 17, arg1. Sorry? It's the 5. And this the type of this argument, int, will be compared with the type of what? Sorry?
Will be compared to the integer method M.
Yes, it will be compared to int x, the declaration of parameter x, which is the first parameter, which is int. So this one doesn't have any subtyping relationship, they're the same, they're fine. So the return type, we can safely assume it's going to be because the types of the parameters have been validated. Okay? And that's it. Why am I copying this twice? Okay. Last slides to do. Oh no, again, I'm an idiot. Because we are running this. Okay, but this is not so interesting. Now, on the heap, location 1, what is the concrete type of it?
C.
Yes, so this one here is a C. So if C, B, and A had actual parameter, had actual fields, what fields would we see here?
All of them.
Sorry?
All of them.
All of them. Those of C, those of B, and those of A. Okay? So that's also how you can distinguish what you have. Okay. Now, oh, the code here does work. For what reason? Look at lines 16, 17, and 18.
Because you didn't say A at 16, but you make the B.
So at line 16 it's a B. Okay, so what methods does the variable B at line 16 have?
M and N.
M and N. Well, actually it also has O, but can we call it? No, but it is there. Because the variable will be initialized with a new C. But what we're saying is that we restrict ourselves only to the things that we find in B. Okay. Now, yeah, the same thing. So as we run this, we get, as we run the compiler, we get that, yeah, A, B, and C have the same build-up. Then variable B has type B, and so the reason why we can call methods M and N is that variable B has type B, and type B has methods M and N. Okay? Even though variable B is actually constructed as an instance of C. Okay? As you, on the other, yeah, and the rest is the same. But as you go on and run this, as you initialize it, then this here has type? No? C. This is a C. Okay? So it has potentially, or it contains inside it also method O. But the compiler prevents us. The compiler forgets this information. The compiler on purpose forgets this information. Okay, and the rest is just the method code. This, look it up, look it later yourselves. Or in, yes. Okay, now, so here's another example, which is very important. This is where the compiler and the runtime do not agree with each other. Suppose we initialize a variable of type B, but with a new C. On line 17, we will get a compiler error. Because O is not a valid method that you could call on a variable of type B. Let's go. Oh, yes. And the same in Java. Even though, if you ran this in Python, would it work?
Yeah.
Because Python would just check at runtime, do you have a method O? Yes, you do, so let's call it. Okay? Good. Now we take a break. Do you want to take a break? Wait a second.
Yeah, please.
Are you sure?
Yeah.
Okay. We now move on to interfaces and polymorphism. So specifically, the subtype relationship can start from a data type which is so general that it has no concrete implementation. Just a sort of empty shell that guarantees that a bunch of methods will be there, but without even providing a default implementation. This data type, which by itself is like the shell of a class, is called an interface. Interfaces are just like classes, defined with the keyword interface. So instead of saying class, whatever, we say interface, whatever. They have no fields because they're not concrete, and all their methods have no body. We say that a class does not inherit from, but rather implements an interface. And a class might implement one or more interfaces, well, 0 or more interfaces. So, in comparison with classes, where a class can only inherit from at most one class, with interfaces, a class can implement 0, 1 to 50 interfaces. Interfaces can also inherit from each other. So, interfaces are a powerful way to say that something that is given as a parameter or in a given context respects, has a bunch of methods at the very least, but without saying anything else about what it concretely means to implement it. And with interfaces, we also do not have to give a default implementation. Now, implementing interfaces in C# requires very little code, so in C# we simply put a colon with the name of the implemented interface is next to that of the defined class. Whereas in Java we use the keyword implements. A bit more verbose, but also a bit more in line with the literature. So, this here is what defining and implementing an interface looks like. Lines 1 to 3 define interface A as something with a method M. Method M will take two parameters. This of type A, an int, and X of type int, and returns an int. Now, what does M do? What does it do?
It's not defined.
It's not defined. We don't know. We do know that it will take a this of type A, an X of type int, will return an int. That's it. No idea whatsoever. Then we define class B, which implements A. Now B, being an actual class, is required to have an implementation, a full definition of all the methods in interface A. So specifically, we see that we have a method M that takes two parameters. They are
This.
of type. Of type? No. This of type B. But is that a problem? No, because what we just said is that every B is also an A. So if here we're saying M takes a this of type A, and here M is actually defined to take a this of type B, it's not really a problem. Because we can automatically convert without loss of information. Then, on line 9, we declare an instance of the interface. We call it B, we initialize it with a concrete instance of B, and then we call B.M. Does this work?
Yeah.
Obviously. And, well, the declaration of B specifies that the type is A. And obviously we can assign the new B to a variable of type A because new B is more specific than A. Oh, in Java, obviously, if you notice on line 4, the double point has become implements. For the rest, it's absolutely the same. On the other hand, this program here would not work. Why do you think so?
You can't create an instance of the interface.
So the class.
But why? You are just repeating something that you learned last year. But the point is, I'm asking you why? Why doesn't line 4 make sense?
Because it doesn't have a body.
Yes, because there is no body to call. So what we're saying here is that we try to build a concrete instance of A, but then when on line 5 we call A.M, where are we going to jump? Now here, it's quite obvious where we're going to jump with B.M, right? We're going to jump to line 5, because on the heap, what we know is that we have to jump on line 5, because concretely at runtime, it's an instance of B. But here, where do we jump? Even if we had concrete implementations of interface A, we wouldn't know where to jump. Now, in Java the same thing would make no sense. Obviously. Now, the same sort of polymorphism can be used quite obviously, but this is just this is not another concept. This can also be used, obviously, for the parameters of what we give. So, why does the program here work? So look, method M of class B takes an A as input and returns an A as output. On line 10, what do we give as a parameter to method M?
New B.
It's a new B. So what is the type of the new B that we give to M? value B is obviously a B. But what does M expect? It expects an A, but we give it a B. Is the conversion safe?
No.
No, because there's another A and A. A B.
Are you sure?
It says public A. Yeah.
So, here, we give a B. But here, we expect an A. Is it safe to give a B where we expect an A? Who says yes? Who says no? You have to pick one. What do you say? Yes or no? What does your heart tell you?
I think yes.
Sorry?
Yes.
Yes. Yes, this is going to work. We give a B or we expect an A. It's fine. Because every B is an A. Not every A is a B. So, do we know here on line 6 anything about X? Do we know if X is going to be a B? No. But we do know that it's going to be something that implements A. Now, on line 6, what is the type of this? Guys, what's the type of this on line 6? It is B. But what does method M need to return? An A. And is that safe to do?
Yes. There's
Why?
no loss of information, right?
Sorry?
Because there is no loss of information.
Because every B is an A. So we should return an A, but we do return a B. Is that fine? Absolutely. Because we have given something with more information than what is required. What is required is just an A. When we give a B is an A plus more information. So we can use this kind of mechanism absolutely wherever we want. Now, I would like to show you one concrete example of this mechanism in action. No! Okay. I felt a flash. Okay, so list, empty, and node. I want to reveal something that looks a lot like. What's up? What's up?
Yeah, well. All possible combinations.
Now, let's define a list of integers. Now, if you remember, in Python, I'll delete the rest. In Python, what we had done was define a class empty with a method is empty, which did what? What did it return?
Always true.
No. Okay. Then we had a class node with a method is empty, which returned false. Inside the class node, what we had were x of type, well, at the moment, let's say int, which is the current value, and then the rest of the list, which was called XS. Okay. Now, what is the type of XS? Is it a node or is it empty? The aplomb. You actually have to admire the nonchalance. Nicely done. Okay, so dealing with unexpected circumstances, +1. Now, what is XS?
Both.
Sorry?
Both.
Both. It could be both an empty or a node. So more specifically, what is XS? Is it perhaps a list?
Like access data.
Is it just a list? The remaining list? Yes or no? Yes, it is. It's just a list. So we might have the temptation to say that this is a list. Now, is node a list? Is a node a list? Are all nodes a list? Yes. Every node is a list. It's one of the ways to build a list, by putting another element. So the node is a list. Is an empty list a list? Quite obviously. So the list is just an interface which right now only has, one method, which is just empty. Oh, it's not public, because in the interface everything is by default public. Now let's add a constructor to the node. Public node int x list access this.x is equal to x, this.access is equal to access. Okay. Now let's add something else to the interface list, like for example a method. Come on, an interesting method for list. Sorry?
Events.
Map? Did someone say map? Did someone actually say map? Oh, come on, let's go simpler in the beginning. Count. So what does count return? Obviously, an integer. Right? Okay. Now, notice that he's complaining. He's saying that, well, we're missing an implementation for count. So what is the count? What is the number of elements of the empty list? 0. What is the number of elements of the list node?
At least one.
At least 1. So 1 plus. Sorry?
Normally node of tail.
I called access the tail.
Yeah.
So
What was access?
almost.
Access dot count.
Yes. Access.count. Access contains the rest of the list. Right? So let's try building a list. List L is equal to new node. New node of 1, then new node of 2, then new node of 3, then new empty. Do I need to add a constructor? No. Okay. And then we could say console.writeLine L.count. And what this does is very simply print 3. Now, here, when we invoke access.count, what is the type of access? It's a list. So, when I call access.count, will I go back to line 32 or will I go to line 19? Yeah, but what is the type of access? Is it node? It depends. The type of access is, well, the type of access is actually always list. So what is in access? It could be, in our implementation, one of two things. A node or empty. So when we call access.count, do we know if access is a node or an empty? No. It could be both. Well, it could be either. So as we call access.count, we might jump into line into line 32 again, or line 31 if you prefer, or we might jump into line 17, 18, right? Do we have any way of saying? Do we know which one? Just by looking at the code here.
It first checks is empty.
Sorry?
It first checks if the access is empty, so
Who checks it? The thing is, in the heap, there is somewhere written access has type list, but concretely, when we create it, we know if it's an empty or a node. So when we call access.count, what is done by the C# or Java runtime environment is we check, okay, This is a list. So, what was it actually? Was this a node? Then we jump here. Was this an empty? Then we jump there.
If you say is empty, return false at the bottom. Line 3.
Look, we don't even need it. The check is empty is done automatically by just saying access.count. That the runtime is checking for us. If it's empty, then we go inside empty to call count. If it's node, then we go into class node to get the method count. So, do we need isEmpty as an implementation? Why? Do we need it for count?
Yes.
Your tone of skin is getting redder and redder. You know? We don't need it, because the choice is made by the virtual machine, by the runtime environment, because the choice is made there, the selected thing. That is a way to make a choice.
This is a form of recursion, right?
Yes, but with the choice. So that is implicitly making the choice if you're going to line 17 or you're going to line 31.
You need to leave line 36 away.
No, we couldn't. If we did, then we would get a red worm of annoyance that says that node does not implement method is empty. Because when you implement an interface, then you have to implement every method of it. So if we want to remove is empty, which could be done, then we have to remove it from here, then we can remove it from the concrete implementations. Okay?
Can you also give an attribute in the interface?
No, you cannot. Sorry. Now, something else we can do is, well, something that looks very, nah, I'm not going to show you today. Okay. So, oh, yes, this is pretty. So, let's make a method prettify that returns a string. A string that shows the content of the list. Now, obviously, he's complaining here, and what is he saying? What do you think it's probably going to say?
It's missing prettify.
It's missing method prettify. So, what is the prettify version of the empty list? Imagine you're, I don't know, my daughter puts little hearts everywhere she can. So, we close off the list with a little heart, right?
Fuck you.
Oh, come on. A bit of poetry in life, seriously. Now, on the other hand, here, to prettify, well, what are we going to put?
Number.
Current number, which is?
X.
Which is x, yes, dot to string, to convert it to a string, followed by?
Comma. Space.
Comma, space, okay.
That's it.
Okay.
No. Plus pretty access dot prettify.
Yes. What does the last bit do? What does access.prettify do? Yes, whoever wants to answer.
Next.
I'm wondering what that motion like this. I hope that you please tell us you put your phone away.
That's your. It's prettifying your slides.
I mean, it's a nice course, but not that nice. Now, what does access.prettify do then? Because you just came back from a sort of passionate trance. So tell us, what does there on line 46 access.prettify do? Where does it go? Does it go back to line 44 or does it go to line 25?
Probably depends.
Shh. you just reached a
I
mystical.
didn't know.
Yeah, but you just
So-
reached a mystical connection with these materials. Don't bother you.
I bet it is 44.
You bet wrongly. Where does it go? If it doesn't go to line 44 for sure, where does it go?
25.
You are wrong again. Where does it go?
Access.
Access.predefine. There, I'm going to select it to make it easier. Oops. Where does it jump? Line 44 or line 25?
Is 34 an option?
Please scream it.
Either.
Either. Because access declared on line 34 is a list. So is it an empty or a node? Sorry? Yes. We don't know. It might be either. So if access, it could be empty. So if it's empty, it's going to go on line 25. If it's node, it's going to go on line 44. So is that in essence an implicit hidden if statement? If you're empty, go on line 25. If you're node, go on line 44. So, implementation of interfaces is a way to automatically provide a choice. And the choice is one of the many ways we have, but a very powerful one, to express conditionals. And with this pearl of wisdom, we can go back to the slides. Now, so through polymorphism, it is possible to pass different data types to other contexts as long as the conversion is safe, as long as we don't lose information, or as long as we don't have to invent new information. Now, inheritance and implementation of interfaces are the basic mechanism for us to extend the polymorphism of the language, which otherwise would just be limited to ints and floats. And by interfaces, we can make this even more powerful by allowing using polymorphism, but without even having to specify a concrete data type. And with this, Dobby is a free app. Now, these materials are all the materials that might happen in the exam. So next week, there is another lecture